Okay, salam alaikum again. We carry on with same part two of photochemistry. We up to this page is about what's happening the molecule after absorbing a photon. What consequences happen to the molecule after absorption of a photon? So after absorption photon by molecule, new species form. These new chemical species could be like the molecule can fall apart, يعني split it into more than one part, or it rearranged to make a new structure. So it means we have a change in the structure, or it combine with another or other molecule, make a combination with another molecule, or transfer electrons or hydrogen atoms or protons or their electronic excitation energy to other molecules, means transferring energy. So either we have splitting, fall apart, or changing the structure. So we have a new structure, or it make a combination with another molecule, or transfers electrons or their energy to another molecule. That's what's possible to happen to the molecule after absorption of photon. I mean, after absorption of a certain wavelength of light. So most photochemical reactions can be considered to occur in three stages. The first stage is absorption of electromagnetic radiation to produce electronically excited state. So the molecule absorb that electromagnetic radiation, and I mean electromagnetic radiation could be something like visible, could be something like UV, and it transfer a change to a new state which is called excited state or transition or intermediate state. All these words are meaning the same thing. And then primary photochemical reactions involving excited electronic states. So sort of a primary, remember the primary photochemical reactions involve excited electronic states. Then secondary, or we call it dark reaction, whereby the products of the primary photochemical reaction are converted to stable products. And why we call it dark reaction? Because then it happens without light. It's like a final reaction, a final change. That doesn't need light because the light is already absorbed and has its function. So we have remember the process for photochemical processes is like three steps. The first step is absorption, and the second step is excitation, and then we have a conversion. As we said, conversion could be something like we said here. If you remember just now, these different changes can happen. Right, in this diagram, you can see we have like a molecule. That's a molecule at ground state. This is the ground state, let's say, absorbed energy. So it jumps molecule excited state after absorption of this photon. So a change from one level of energy to another level of energy. This level of energy, which is the original one, is called ground state. And this one is called the excited state, which has higher energy. And then that excited molecule goes certain reaction, as we said, and that's called primary photochemical reaction. Look at this one, R star. So this stage number 2, this is the excitation state, and this one is the absorption state. So we have absorption of photon, molecule, jump to higher level of energy, and then It makes, it forms sort of intermediate stage, something like transition state, which it doesn't take long, it doesn't stay for a long time. And then that excited state change to product, goes to product back. Look at this one in the primary. That primary, we have a transition at higher state, and then it goes back to its ground state by giving product, by giving different products as you see in this diagram. Products of the primary photochemical reaction are converted to stable, look at the stable products. So it will be at the end as a product and it's stable. It's not excited anymore. That's it. The reaction, the change has finished. So we have reactant, then we have a transition state, and after that we have the product, and that's it, the photochemical reaction has finished. So what are the features of photochemical reactions? يعني something like مواصفات أو صفات features of chemical reactions. يعني إذا نريد نترجم feature هي مميزات، يعني بماذا تمتاز. So what are the features of photochemical reaction? Number one, they don't take place in dark because it's photochemical reaction, obvious from the name. So it means it happens only when there is a light, when we have a light. We have a certain wavelength for that reaction to happen. So that's why we call it photochemical. Otherwise, it doesn't happen in dark, but take place in the presence of light by absorbing it. I think this is very clear. Number two, since different colored radiation in the range of visible light have different frequencies. Of course, when you have a visible light, the same visible light has like that's red, has violet. So they have a different wavelength. So it means they have different frequencies. In other words, they have different energies. So they have different energies. Since different color radiation in the range of visible light have different frequencies and hence, of course, different energies, therefore, all radiation may not be able to initiate a particular reaction. So it could be one color initiate the reaction, but the other color doesn't because the energy could be low. As we just explained today with different wavelengths. So for example, a photon of violet light has highest frequency and hence the highest energy. Hence a reaction which is initiated by violet light may not be initiated by other colored radiation visible light. الفايولت هو يكون طبعا اعلى انرجي بالفيزيبل والريد هو اقل energy. So if a reaction initiated by the violet part of the visible light, it could be, we're not saying necessarily, it could be, it doesn't initiate by the red light of the visible, the red part of the visible. On the other hand, the photon of red light has lowest frequency and energy, therefore a reaction that can be initiated all other radiation as well. طبعا, if the reaction initiated by the red, it means it must be initiated by violet يعني الفيولت already هو أعلى من الريد فإذا reaction initiated by lower energy طبعا obvious it should be initiated by higher energy. بمعنى أنه if we have a reaction initiated by the violet part of the visible, not necessarily to be initiated by the red, but العكس, the opposite, if the red part of the visible light initiated the reaction, it means the violet must initiate the reaction as well, because the violet has higher, greater energy than the red. Number three, what are we saying? Sorry, number three, let's go to number three. I think it's on the next page. So temperature has very little effect because it's already the photochemical. We're not saying temperature has no effect at all. No, temperature has a very little effect. It's not like the thermodynamic reaction, the exothermic and endothermic reactions. In this case, with photochemical reaction, temperature has very little effect on the rate of photochemical reaction. Instead, the intensity of light has marked effect. Remember, intensity of light, it means the number of photons. So you have more photons, it means you have more molecules absorbing that energy. طبعا على شرط in condition that energy of the photon is enough to initiate the molecule. يعني إذا أنت عندك you have a number of photons, high intensity of photons, but the energy is not enough to initiate the reaction, so we don't have a photochemical reaction. But if you have enough energy for the photon, the photon has enough energy, and you increasing the intensity, it means you have more photons having enough energy to initiate the molecule. So in this case, we have more molecules will be irradiated, will be initiated. It means that time the rate like the reaction will increases. Number four, the free energy change of a photochemical reaction may not be negative. But remember, in thermal reactions, we have delta G, and that delta G should be negative for that reaction to happen. For that reaction to happen, the energy must be negative for that reaction to happen. But in photochemical reaction, that's not necessary. That's not necessary. Number five, there are many substances which don't react directly when exposed to light. However, another substance is added, the photochemical reaction starts. And هنا we add something else to that molecule, and that molecule will, the other molecule, you add it, absorb that energy, and then transfer it to the molecules to make a transfer. Go through these differences between photochemical reactions and thermal reactions. Let's go through these differences between photochemical reactions and thermal reactions. Let's see what we're having in this table. It says photochemical reactions. These involve the absorption of light. I think we know that by now. These involve the absorption of light. In thermal reactions, these involve either absorption or evolution of heat. So we have change in heat. Either is giving heat out or it's taking heat in. That's in thermal reaction. While in photochemical reaction, we have absorption of light, not heat. Number two, with photochemical reactions, these reactions take place in the presence of light. I think it's obvious. Photochemical reaction needs light. It doesn't happen in the dark. While in thermal reactions, these reactions can take place in the dark or in the presence of light. Doesn't make difference. With photochemical reactions, the reactions are particularly independent of temperature. As we said before, even if the temperature, if it has an effect on the reaction, but it has very, very little effect, while rate of such reaction is not affected by the intensity of light. It's nothing to do with light with thermal reactions. Number four, with photochemical reactions, what we're saying, rates of these reactions are dependent on the intensity of light absorbed. As we said this today, as we say, the intensity of light means you have more photons, more number of photons, so you have more number absorbing that energy required to initiate. The free energy change for reaction is always, in this case, negative, and the rates of such reaction is not affected by intensity of light. It doesn't nothing to do with light because it's thermal reaction. Okay, right. What we having here, the free energy change, I said, it may be negative or positive. In this one, with thermal, it should be negative. Photochemical activation is highly selective. That is, absorbed photon of light excites only a particular atom or molecule or a group of atoms, which then becomes the site for the photochemical reaction. And each group, each atom, it has a certain values of a certain wavelength to be absorbed. Thermal activation is not of selective nature. Doesn't mean it's selective. So with thermal, we don't have selectivity, while with photochemistry we have selectivity. So something is called quantum yield. We need to understand what we mean by quantum yield in this case. So even though a reactant molecule absorbs a photon, the excited molecule might not form products. This is, I think, it needs a good consideration. So when we have a molecule absorbing the photon, yes, but it doesn't mean definitely the excited molecule make a product. Not definitely. There are many ways in which the excitation may be lost. So probably we have an excited molecule, and that excited molecule doesn't give any product. And that energy which is absorbed be lost by some way. So therefore, we speak about quantum yield. If you remember in your chemistry study, we have something called yield. When you have a reaction, theoretically, we must get 100% of yield. But for so many reasons, as you know, you don't get that 100% of yield. Always, it is less than 100%. There's many reasons for that, and it's not our point at for time being. So you have an idea about the yield, and that yield, it's like a percentage. We say, for example, 70%, 80%. It means instead of you getting 100% products as calculated theoretically, but practically you don't get that yield. Always it is less, as we said. So similarly, we have something called quantum yield, and it is symbolized as a phi, which is the number of reactant molecules producing specified primary products, could be atoms or ions, for instance, for each photon absorbed. So how many photon absorbed and how many we get is similar to the yield for normal thermal reactions. As a result of one successful initiation, many reactant molecules might be consumed. So what we're saying, as a result of one successful initiation, we're not just saying initiation, successful one, which it gives a product, many reactant molecules might be consumed. Consumed يعني يستهلك. So the overall quantum yield, the number of reactant molecules that react for each photon absorbed. Suppose you have 100 molecules and 100 molecules, so the number of reactant molecules that react for each photon absorbed. Look at here what we say. We're saying that react. We're not just saying absorb. We're saying react. Because as we said before, absorption of light by a molecule doesn't mean definitely there is a reaction. Not necessarily. So suppose you have 100 photon and you have 100 molecules, but 70 or 80 of these molecules make a successful absorption, a successful initiation, a successful product. So you have like 30 of them, sort of, they lost the energy. So in this case, we're talking about yield. We call it the quantum yield. So it is defined as the ratio of number of molecules reacting in given time to the number of quanta absorbed in the same time. So how many photons absorbed within certain time and how many molecules reacted and responded to that number of photons. But why sometimes we have some like phi less than 1, yani less than 100%? Number one, the product of primary process may colloid with second molecule and transfer energy, second and third, so on. Thus, chain reaction starts and number of reacting molecule will be high. يعني كأنه one molecule transferring energy to other molecules. So we have more than one molecule reacted. That's why in this case we have phi quantum yield higher than 1, يعني higher than unity, higher than 100%. The other reasons due to formation of intermediate product which act as a catalyst. Sometimes the intermediate formed in this absorption of light, that intermediate act as a catalyst, speeding up the reaction, giving like more or higher rate of that reaction. Number three, exothermic reaction may activate more molecules. So these just are reasons why we sometimes having phi greater than 1, which is not accepted theoretically, but there is a reason. That's some of the reasons. And why sometimes we have phi less than 1, less than 100%. In some reaction, deactivation of activated molecule take place in the primary process before transfer of product. I think it is very clear. You have the activated molecule, it's absorbed the energy of photon, yes, but for some reason, a deactivation happened to that molecule, to that transition state, so it doesn't go to the product. It's end there, that's it. Stop. Number two, the product of primary process may react back to form reactants. Same primary process, the intermediate stage, it goes back to the molecule for some reason. Giving you an example, the composition of hydrogen iodide and hydrogen bromide, polymerization of anthracene. These are just examples. So what factors affecting the quantum yield? All primary photochemical process is endothermic, hence quantum yield increase with temperature. That's another factor, could increase by temperature. Although we said before temperature has a little effect, we didn't say it has no effect, but it has a little effect. And that's why when we increase the temperature, the photochemical reaction could increase. If you remember, photosynthesis is an endothermic reaction. It's an endothermic reaction. We know energy absorbed by a molecule is inversely proportional to wavelength. Remember, this is inversely proportional, not directly. And in other words, with lower wavelength, we have higher energy. Hence, quantum yield will be higher at a lower wavelength and vice versa. So it means if the light has higher energy, more energy, in this case, you have higher quantum yield. As the speed of photochemical reaction is proportional to intensity, if you remember, we said this before, it's in, directly proportional to intensity of light. And just to remind you what we mean by intensity, we mean the number of photons. We don't mean the energy, we mean the number of photons. Quantum yield increases with intensity and vice versa. Vice versa يعني والعكس بالعكس. Okay. Photochemical yields decrease with increase of pressure and with addition of inert gases. Something related. Okay. In the photolysis of HI, for example, there's this one. You have HI light. You get H star with I star excited, and then that H star with another HI molecule, it gives H2 and I star. This is equation 2. So it means 2 moles of HI destructed 1 mole of 1 mole in equation 1 and 1 mole in equation 2. Right, so I plus M give I2 plus M star. Overall reaction, it's 2Hi, 1 photon, giving H2 and I2. Look at 2 molecules, in this case, initiated by 1 photon. So the overall quantum yield is 2, supposed to be 2, supposed to be double, because 1 photon initiating 2 molecules to giving 2 molecules. So as you see in this example, the overall quantum yield is 2 because the absorption of 1 photon leads to the destruction of 2Hi molecules. So 2 molecules, reactants, which is Hi, destructed by 1 photon. The chain reaction, phi may be very large. When we have a chain reaction, of course, chain reaction means so many reactions, so many products happening with one starting molecule. May be very large, of course, in this case, phi, the quantum yield. In such case, the chain acts as a chemical amplifier, يعني مكبر, يكبر, of the initial dissociation step. So again, quantum yield, phi at certain lambda, for a lambda, number of molecules decomposed, divided by number of photon absorbed. Very simple. So lambda is the wavelength of the photon at which the photon absorbed. Quantum yield has no unit because it's a ratio between two numbers, has a no unit. So this example showing the quantum yield for the decomposition of a reactant molecule in a decomposition reaction is defined as, sorry, this is the source, this number of photons, this is the sample, photons out, and we have a detector, so we can know number of photons out over number of photons in. How many out, how many in. Again, that's give you an idea about the quantum yield. It's not all photons are absorbed productively, and مو كل الفوتونات giving product. The typical quantum yield will be less than 5, less than 1. يعني التيبيكال النموذج المثالي يعني هو يجب أن يكون phi أقل من 1. But sometimes phi is equal greater than 1 for some reasons, as we said today before. Let's take this example. It says when a sample of 4-heptanone was radiated with 313 nanometer light. Remember, you don't use this figure. 3.0, that's just giving you the lambda with a power output. If you use this one, you use it might for calculating, some calculating, sorry. So 313 nanometer light with a power output of 50 watts. Remember, that's intensity. The conditions of total absorption of 100. So you have a time. It was found that 2.8 times 10 to the power minus 3 mole ethene was formed. So this is called Norrish reaction. This is called Norrish reaction. So what is the quantum yield for the formation of ethene? Okay, first calculate how many photons, because we need to know how many photons. As we remember, we said quantum yield is number of photons. The number of photons, how we can find it out? We have energy divided by h nu, and that means p power times time, or energy means time, and powers times time divided by h, and nu is equal c over nu. So we have lambda p t over h t. Do we have lambda? Yes, we have lambda. And remember, lambda is in nanometer, so you should convert it to meter by 10 to power minus 9, and then you rearrange how to write it. It is 3.13 times 10 to power minus 7, and this is of course in meter, times, do we have the power? Yes, we have this joule per second, and you have the time, that's the time, 100 seconds, divided by Planck's constant. This is Planck's constant, this 1 joule second, times speed of light. This is speed of light, meter per second. So we have the units meter, joule, second, meter, second. So we don't need any conversion in this case. And of course, this meter will cancel this meter, and this second will cancel this second, and this second will this second, this joule will cancel this joule. That means we're working correctly. So we have this number, and look at this number has no unit. So that's not the number of photons. So this is the way you need to find out the number of photons, how many photons you have. What's the total energy divided by hν for each one. Now you need to calculate how many mole of photons, how many moles of photons. That's the number divided by Avogadro's number. Of course, you get the number of mole of photons. You need to convert it number of moles. And now divided number of ethene in moles, because given produced by the number of photons to get the quantum yield. So mole of ethene divided by mole of photons. This is the number of mole of ethene given in the question, and this is the number of photons you found it out just now. You calculated this now, so you get something like 2.14. That's yield. If you don't convert them to number of mole, you need to use both of them. I mean, the mole of ethene and the mole of photon, just as a number of ethene without number of mole, and the photons should be number of photons without number of moles. So number to number as number of molecules is okay, or mole to mole. Remember this point. You should convert them either both to mole or both as a number, this number. If you have in the question one in mole and one just in number, you need to convert one to other, make units consistent with each other. This is another example. Calculate the number of photons emitted by 100-watt yellow lamp in 1 second. Take the wavelength of yellow light as 560 nanometer and assume 100% efficiency. 100% efficiency, and the work is okay, no problem, nothing lost, all absorbed and all okay. The solution number of photons, again, lambda pt over d. You have lambda, remember to convert it to meter, and you have the power, which is 100 watt, and you have the time, which is 1 second, that's 1 second, divided by h, this is Planck's constant, 6.6 times 10 to power minus 34, times c, which is the speed of light, this one, so you get this number of photons. Because the question says calculate the number of photons emitted, how many photons emitted. It's not asking you about the quantum yield. Sorry, excuse me. You have two exercises and you have the answers for them. Sorry. It's supposed to be three exercises. This is one, this is two, this is be three, this one should be three. Anyway, that's a mistake. Again, what we're saying, photochemistry is concerned with how light interacts with matter and initiates chemical reactions. So it's a matter of light reacting or interacting with a molecule and what would happen to that molecule, what a product is given, what change would happen. That's photochemistry. Okay, I think we stop here. This is again explained for you. We carry on next session with that. Okay. So far, thank you very much. And we will carry on with the rest of this part of photochemistry.